Now, the nice part about this is the first step is that it's the same as an absolute value equation, those single ones that we just took up and that we did the previous day. So you split it up into two cases, the one where the argument of the absolute value is less than 0, and the one where the argument of the absolute value is greater than or equal to 0, or you can include either side. And then kind of just solve normally. It's the interpretation in the end that's going to be very different. Okay, so we'll set that up. So we've got 2x plus 3 less than 0. And again, I'll encourage you to remember why we're doing this. So when I solve this and I move the 3 over, it becomes negative. I'm dividing by a positive, so I don't flip the sign. Again, like we talked about, sometimes you might want to, this one's kind of an easy fraction, but maybe you want to turn it into a decimal so that you know for sure on a number line if, like, where you are in the interval kind of thing. If the argument of the absolute value is less than 0, then what do we have to do when we go to solve? We have to, very good, we have to multiply what's in the absolute value and only what's in the absolute value by a negative 1. Why? Because that's what the absolute value operation does. It flips things to positive, and we have defined this as the interval for all values of x that will make the argument negative. So in all those cases, we can multiply by negative 1 to flip it back to positive because that's what it does, right? And again, that was kind of new thinking. And then we can do separately as our second case. Like I said, you have to include one side or the other. And in this case, we don't multiply by a negative 1. We leave it alone. What do you think is a common mistake here? Anybody have an insight?
Ooh, getting rid of the inequality part and just putting equals.
Oh yeah, good. That's not what I was thinking, but yep. Not recognizing that this is still an inequality. Yeah. So the one I'm thinking of would happen on this side.
Using the same
Inequality.
sign for inequality from the top to the bottom.
Yeah, so that's exactly right. You have to recognize that these are not linked in any way. This one comes from the case that we defined as we split up the two cases. This one comes from the question. So they're totally separate. But again, that might make sense right now, but then you're rushing and you're kind of like getting stuff mixed up and you're thinking about something else that's maybe more complicated, and then you make some kind of smaller mistake like this, which does end up having a big impact on the question. Okay, so something to just be conscious of as you're doing the practice, that this sign always comes from the question, and then the cases above are separate, and you're defining those cases so that you can interpret your answer in the end. Okay, okay, now we just solve them, and there's nothing different here. It's the same kind of solving. So I'm moving the 3 over and the x over. Once again, what do I do when I divide by negative 3?
Flip the sign.
Good. So we can see how, like, if you are good with fractions, you may not need this, but you can see how 3 over 2 and 8 over 3 when you've not been working a lot with fractions, might not be super obvious which one's bigger, which one's smaller. So the decimal absolutely clarifies that, and we can tell that it's in the interval. That being said, it's more complicated than just, is it in the interval? That's not how this works, this interpretation. So we're going to get to that in a minute. So we'll solve the other one. So I move the x over, and I move the 3 over, subtract 3 from both sides, subtract x from both sides, and I get that. Okay? In order to solve these, we're going to use a number line. Multiple number lines, actually. And there are lots of different ways. I would imagine different teachers have slightly, well, I know that different teachers have slightly different methods about how they do these things. The specific method is not what's important, but, don't just magically come up with your own. Either follow mine or make sure you come up with one that is as good. Okay. First thing, we take all of our values. So that's the negative 3 over 2. That split up our intervals here and each of our solutions. So negative 8 over 3 and 2. Okay. So negative 8 over 3 is going to be over here. Negative 3 over 2 is going to be in the middle. And 2 is going to be on the outside. Whoops. And now I have to manage each case separately. And then in the end, we're going to combine them. Okay. So if I'm looking at this first case, all numbers that are greater than, strictly greater than, not greater than or equal to, right? Strictly greater than, again, that just came from the question. Negative 8 over 3. And also in the interval, which means less than negative 3 over 2. So what are all those values? Greater than negative 8 over 3 and less than negative 3 over 2. So this one specifically is greater than, so there's another little bit of a new notation here. These are open circles because they don't include the point. This is a specific mathematical notation. I'm using an open circle, an empty circle. If we were including the point, we'd color it in. We'll see that in another example. But I'm not including it, so it's just an empty circle, not colored in. Okay, we call that an open circle. So this solution means all the values greater than. This interval is all values less than. The solution from that case is the overlap of those two. Where do they overlap? Some of you are going to be able to go straight to the answer. You're just going to kind of get it. Some of you might like to split them up separately and think about the overlap. Okay, so as you're going through it, you got to kind of determine your comfort level, how you like to approach it. But I can look at each of these separately. X's that are greater than negative 8 over 3. As long as I've got these lined up properly, again, just thinking about the decimals, if I have something on the wrong, like a number on the wrong side on the number line, again, everything falls apart, right? So everything greater than negative 8 over 3 is all the numbers going that way. Less than negative 3 over 2, because that's the defined interval. Starting at negative 3 over 2 and going less than, and look where they overlap, right? So it's all the values that are in that interval. You could pick a number in that interval, sub it into the original equation, and see if it works. What's a number in that interval? Oh, good. Yeah, negative 7 over 3. That's a safe one. There is an integer number in there. Negative 2. So Sometimes with fractions, it can be a little bit tricky. Some of the fractions are going to be even less friendly than this, possibly. You know, if you can find a number, maybe there's an easy number like 0 in there or something, you could sub it back in and just do a double check kind of thing, right? Okay, next one. So I like to do one of the cases kind of on top and the other case on bottom. So values that are less than 2. In the interval of values that are greater than or equal to -3/2. So again, just because of how this works, we have to include that in one or the other of the cases. So notice how I've colored it in, and it's greater than or equal to. So what is my solution? Well, this point is included here and also included there because that interval goes through it. -3/2 is in that interval. Do you agree? So I'm including this point to there. Because, yes, this one continues on, but this one doesn't. That's where it stops. So that's my solution for that case. So for this side, again, notice the difference that I've included one side of the interval but not the other. And that's because of how we set up the cases. And for this side, I've got that solution. Everybody good so far? Any questions about any of that? We're going to do a bunch more examples, so you'll see it over and over again, but yes, what my expectation, in fact, we're going to do 3. So we're going to look to see if we can combine them and do a final answer. My expectation, but the main reason for this is because I think it's going to make you most successful, is that you think about each case individually and what is the solution to the individual case. And then we're going to do a second number line. And we're going to see if these cases connect in any way or overlap in any way or anything like that to write a final statement. So this top case goes from here to here, right? And then the bottom case, that's this part, colors in the circle and goes to there. So what's our final answer?
Would it be -8/3 less than x, which is less than 2?
Very good. So we're including this point, but it just connects the two intervals. Sometimes they'll connect, sometimes they won't. But it connects the two intervals so we can write it as a single statement. I also like doing this like with these number lines and kind of doing all the different things separately just because it really does force you to think about the different intervals that are involved and how they overlap and that kind of thing. Yeah?
So it doesn't matter that we weren't including -3/2 in the top case.
Right.
Because it's in the bottom case, it's just.
Yeah, and there's a couple ways that you can think about this. we are like we are splitting it up into separate cases as our strategy for solving this, but ultimately we're looking for the solution to the entire thing, which is this. That's the solution to the original question, that interval. All the numbers in that interval. What's a number in that interval? -2, -1, 0, 1, 1.5. Those are all numbers, and obviously infinite more. In that interval will satisfy the original inequality. But the other thing is, if you think back, like I said, could we have put the equal sign on that side instead of the other side? Yeah. Like you're just choosing which side you include. You could include one or the other, or quite frankly, both. So, that was our method of how we split up the cases. It wasn't necessarily the rule of how you have to do it, if that makes sense. Quickly, visually, here's the graph of this inequality. So this absolute value of 2x plus 3 is that green function. It looks like an absolute value function. And then less than x plus 5, which is that straight blue linear line. So when is the absolute value less than? Well, it's in that location, right? That's where literally the one function is below the other function. And if you think about it, why do we have the two cases? Because we split it up into this case for the left side, which is right there, which is obviously at -1.5. You can see that, right? And then this case, so this side, which is the other side of the absolute value, the other case, and then they end up combining. The visual of this, I don't think is going to be super helpful in terms of solving these. But some people like the visual, some people find it helpful. I think it's worthwhile to quickly look at it, but don't think that it's necessarily going to help you solve these. You really do just need to get the steps that are involved. Split up the cases, define your intervals, set up and solve each case separately, and then those number lines can help us determine the final equation, or final solution. Okay, so again, we're just looking at the argument of the absolute value when 6 minus 3x is less than 0, when 6 minus 3x is greater than or equal to 0. So we talked about this before, the sign flipped. So some people might think this is the side that you leave alone because now it's greater than 2. But no, it comes from the first step, that first line that we defined this case as the case where the argument of the absolute value is less than 0. We don't care if x is less than 0. It's the argument that's less than 0. So this is the one that we make negative. And again, look at how my sign matches the sign in the original question. So we're flipping back and forth. Like I said, when you're doing all kinds of other things and thinking about other things, that can be a problem. It seems simple, but your brain just mucks something up, mixes things up, and you end up making a mistake. And then this side, we leave alone. Okay, so you can go ahead and solve those on your own if you like. Equals intervals. Whoops. So I got 5/2 and 7/4. Case on the right had to flip because we divided by a negative. On the test, there's going to be just all kinds of questions all kind of mixed together. Single absolute value equations, double absolute value equations, single absolute value inequalities. We don't do double absolute value inequalities. Then also the stuff that we're doing tomorrow, polynomial equations, polynomial inequalities. All of these things have slightly different methods of how to solve. How do you solve a polynomial inequality? That's from day 2 and 3, and it was on the quiz. With the sketch, you do a little sketch and you read your answer off the sketch. How do you solve a polynomial equation? Well, you factor it, and then you just read the answers from the factored form, right? So all of these things have slightly different methods. There's overlap, but slightly different. And when they're all mixed together, it can get confusing. How you interpret your answer, all of those different little things. Okay, so you really got to also make sure that you understand that when they, like each one on its own, you might feel confident with, but when we start to mix them all together, it does get more complicated. So all the little things that you can do throughout to just be careful can really, really help. Okay, so number line. And if you make even a small mistake in the beginning of one of these questions, like on the test, it's specifically designed so that different questions have different kinds of answers, so that you are going to have to demonstrate your understanding of all the different kinds, whether it includes a point or not. What kind of, is it an interval answer, right? Like sometimes even the double absolute value has an interval on which it's true. It's never true here. It's always true here. All those little things. Like the test will be designed to have a little bit of everything. So you got to be careful, because if you do a mistake at the beginning and it changes the question, that's not the kind of interpretation we're looking for your answer. Okay, so it makes a bit of a bigger difference. So again, I think I've said this before. How do you make sure that you're careful and not make a mistake? And of course, nobody wants to make a mistake. Nobody's trying to make a mistake. But some of these little details, just pay attention to them now and take it slow. Don't rush through it. Don't think it's, oh, this is easy. I'll just, go straight to the answer or something. Recognize that they're so important to get correct, because otherwise they change the answer. Okay, so what's the smallest of my 3 intervals? I've got 1.75, I've got 2, and I've got 2.5. So the smallest is 7/4. The middle is 2. And the biggest is 5/2, 2.5. Often this interval is in the middle, but not always. This is another kind of pattern that we often see, but it's not always the case. So just be a little bit careful of that. Okay, so values that are strictly greater than 2. And values that are greater than or equal to 2.5. Where's the overlap? So, right, so this interval includes the point, and this interval includes the point as well, because it runs straight through it. And then they both exist over here. Values that are less than or equal to 2. Values that are less than or equal to 7 over 4, 1.75. So what's the solution for that case? Where do those two overlap? Yeah. Starting at 7 over 4 and including it, very good. So x less than or equal to 7 over 4. Combining these, is starting here and going that way, and starting here and going that way. So there's no overlap? So the final answer?
It would be the two answers on the floor, so x greater than or equal to 5 over 2 and x less than or equal to 7 over 4.
Yeah, good. So we just write them separately. Order, of course, doesn't matter. Just write them separately. Yep.
If you can see the answer without the third number line, you still have to
Yes, you don't even need any of the number lines. So be careful of this, because the number lines are very useful. And it's a strategy that if you start to feel like you're getting good at this, and you're kind of jumping to the answers, but then all of a sudden, for whatever reason, one is weird and you get stuck, this is the strategy that you can fall back on. So I would strongly encourage you to try it a few times and get used to the idea of these number lines. We use these kinds of number lines again for other things throughout this course. So it's something good to just get familiar with. But some of you are absolutely going to be able to just look at this and say to yourself, what are numbers that are greater than 2 and greater than 2.5? Numbers that are greater than 2.5, right? What are numbers that are in both of those intervals? All the numbers that are greater than the bigger number. And if you can do that, then you can bypass the number line and just say, therefore, x greater than or equal to 5 over 2. Okay, so you don't have to show me the number lines, but you do have to make those statements. And I want to see all three. Each of these two as separate, and then a third final statement of an overall solution, whether it's, I know it seems repetitive, but it only takes like 2 seconds to rewrite it. So one statement altogether, but then each case like done separately, right? Solved separately. Okay. Any questions? We're just going to keep going. More examples. Different, right? Like there's some parts of this that are obviously familiar. The solving of the inequalities, just solving equations. But like that interpretation and thinking about number lines and even intervals as solutions is different. Should feel different. Pretty new. Okay, see if you can set up the cases on your own. So it should look like that, then solve each side. Anybody get something weird happen in the second case? And it feels weird. And you're like, oh, I must have made a mistake. But you didn't make a mistake. No, it happens. Now, whether you get the same exact thing as me or something different, like 0 less than whatever, that part doesn't matter. Okay? Whenever I see the x on both sides subtracting x, I just leave the numbers alone. That's just my habit. But you can move the numbers side to side. Like, that doesn't make a difference. You have to do it correctly because we have to interpret it correctly. But that's not wrong. Like that's the correct algebra. And this is something we have talked about in other situations where we get these kinds of things happening and then we just have to interpret what it means. Okay, let's do the left side first. So that's what you should have so far. Okay? So check that and then we're going to interpret the left side first. So let's see, I've got -1 and 3, and this side doesn't have a number. So I only have 2 numbers on my number line this time. So for the left case, I'm starting with, it doesn't matter obviously which one you pick to start with. So x greater than or equal to -1. So color in a circle, including the -1 and going bigger. And then x less than 3, strictly less than. Where do those two overlap? What's the solution to that case? Yeah, good. So -1 less than x less than +3. Yep, good. X is between -1, including -1, not including 3. Again, I could have included 3. That was a choice that I made when I'm defining those intervals, and it's kind of a random choice, so I could have included it, but I didn't, so try to be consistent, obviously. Okay. On the bottom, I have all values of x that are greater than or equal to 3. -3 less than or equal to 5. How do we interpret that? Any thoughts? Any guesses? Think about that statement. It's always true. -3 is less than 5. Less than or equal to. Some people get caught up, well, it's less than, but it's not equal to. It's not less than and equal to. It's less than or equal to. So it could be equal to, or it could be less than. Both of those qualify. Okay, so be a little bit careful of that trap. It is less than 5, and always will be. So this is always true. How do we show always true on a number line? It's just everything. So what's the solution to this one? If it's where they overlap and this one is everything, then it's just the other interval, isn't it? It's just this interval. So values of x greater than and including greater than or equal to 3. So this solution starts at -1 and includes it and goes to 3, but doesn't include it. And the second solution starts at -3, or sorry, +3 and includes it. So I can color in that circle and continue on. So what's my overall solution?
X is greater to everything, including -1, or everything
Yeah,
above
yeah,
-1.
yeah, no, that's good. Yeah, greater than or equal to and including -1, exactly right. See how there's different kinds of answers. The first one was an interval between two numbers. The second one was two separate intervals that went different directions. This one, they kind of link up and both go off in the same direction. And there are other types as well. You could get no solution. You can actually get all values make it true. There are all kinds of different solutions. Okay, we have 2 more that I think we'll have time to get to. Any questions though before we move on? One other thing that I wanted to mention was, notice how in the first number line that we're doing it in 2 separate cases, it's where they overlap. So they both have to be true somewhere. Whereas this one, we're combining them. It's this one or this one, right? The first step is this and this. Second step is this or this. So you have to recognize that they are different situations. We're combining the two because both solutions to both cases are valid solutions. They don't have to overlap. But this has to overlap with this, and this has to overlap with that. So there's overlap in some situations, but then in other situations we're combining. Okay, I forgot to go over question B. So remember, question B was 2 places, like 2 intervals that were separate. So where is the absolute value above the linear? And so it's above here and above here. So that yellow colored in area is the interval where it's true, right? And in this interval where the absolute value dips below the linear is the only place that it's not true. And then you can get a situation like this. Why was it 2 intervals that combined to go one direction forever? Because this side of the absolute value, which stops here, it's above, starting at a certain point, -1, that was our solution. And then for this value, it's always greater than. Because those 2 sides have the same kind of slope, so they're just going parallel, right? So again, you can start to think about the different kinds of possibilities that you could have with all of these. All right, next one. Like I said, 2 more. So again, try to set these up. So that's what I got. Is that okay? If we wanted to think about this without the number line, values that are less than 1 and less than 2, it has to satisfy both. So it's not values that are less than 2, because some values that are less than 2 are not less than 1, like 1.5 is less than 2, but it's not less than 1. It has to be both. So what's the answer to this interval? All values of x less than 1. So just this is the solution, x less than 1. Because all of those are also less than 2. What about this? What are numbers that are greater than or equal to 2 and less than negative 1? There aren't any. So this case has no solutions. This case is x less than 1, so the solution to this is x less than 1. You would say, therefore x less than 1, no solution, therefore x less than 1. I know it's repetitive and redundant, but I think the thinking there is important. If we did the number line for this, which we're going to do, we get negative 1, we get 1, and we get 2. Values strictly less than 2, and values strictly less than 1. So where do they overlap? And then the second one, values greater than or equal to 2. And values strictly less than negative 1. They don't overlap. Right? Pointing different directions, starting in different places, don't overlap. Compare that to an example like this, where they're starting in different places, but pointing in opposite directions, but they do overlap, cross over each other. So you've got an interval in between where you've got solutions. So no solution here. And you do have to state that, whoops. But that doesn't mean there's no solution to the entire thing, because we did get solutions from the first case. Could you have no solutions at all? Yes, you could. Absolutely. Okay. D. So notice how on this right side, there are no solutions and there never will be, right? The absolute value of the green one will never cross above the linear, the blue one. So no solutions there, but we do have solutions on the other side. Okay, one more. What's different about this one? Anything really? Yeah.
There's like -2 on the side.
So it's got an extra constant. Believe it or not, that can cause problems just because we don't do it as often. The other thing that's different, anybody else see a difference? I mean, it's minor, but again, believe it or not, it can cause problems. The absolute value is on the other side. And so people think it's, don't write this down because it's wrong, x plus 1 less than 0. Well, no, that the whole point is it's because of the absolute value. That's the only thing that you ever have to multiply by a negative. Or some people think there's 2 cases here, and they start doing a number line and doing like x plus 1, x plus 3. Why would you include x plus 1? It's not an absolute value. It doesn't matter if it's positive or negative. It just is what it is. So be careful of that little trap as well, that you are only ever multiplying the absolute value part by a negative. Nothing else in any of these equations or inequalities. So x plus 3 less than 0, which is when x is less than negative 3. X plus 3 greater than or equal to 0, which is when x is greater than or equal to negative 3. So a bit of a different feel to it. We get caught up in these habits of all the questions are kind of the same and repetitive, and then all of a sudden it's just slightly different in something, some habit or pattern that we've, I don't know, developed even accidentally, and you might not be aware of it, but then you use it to solve, and it turns out it's not a real pattern. So just be careful and really think about these concepts and why we're doing what we're doing. That's why I spend so much time talking about this stuff. More interesting results, if you think about it.
Would that also be always true because it's greater than or equal to?
Yes, it's greater than or less than or equal to, or if you do it backwards, greater than or equal to. But this is the kind of situation where we say, well, yeah, it's equal to, but it's not less than. Well, no, it doesn't have to be both. It's or, it's not and. You can't be less than and equal to something. I mean, that's not possible. Think about it. Less than and equal to? No, that doesn't make any sense. So it's less than or equal to. And it's equal to, so yes, this is always true. So if we do our number line, and it turns out this negative 3 is the same as that. So this number line only has one value on it. This is less than negative 3. And this is less than or equal to negative 3. Again, it's where they overlap. So even though the point is included in one, it's not included in both. So it's that. And this one is greater than or equal to negative 3. And always true. Therefore, greater than or equal to negative 3. So what's our overall solution? So this one starts here at negative 3 and goes that way.
We address the x and the y.
Mm-hmm.
It's always true.
And this one includes this point, so I can color it in because it's the combination of these two, not where they overlap. So it's true for all values of x. And that's how we state that x is an element of the real numbers. So take a look. It's below everywhere. And then it links up and it's equal to. And that's what the question said, less than or equal to. So below, and then equal to, and will always be equal to for all values. So you can imagine if I took this line and moved it down, it would also always be less than, but the algebraic solution would look a little different, right? But you would just move it, like, it would have the same overall solution. So visually, it would kind of look the same idea, but algebraically, you wouldn't get this. Think about how we got 1 equals 1. And think about how it's because those two lines are on top of each other. So they are equal to each other. Like that's how the algebra matches the visual, the graphs. Kind of interesting. Any questions? I'll leave that up there for a minute in case you didn't get it all the way copied down. Any questions?
Do you ignore the always true arrow when you're writing like the solution?
No. So the always true arrow, when I'm considering the case on the right, and this is the always true, I think I understand what you're asking. You don't ignore it, but you're looking for where the overlap is. So you're right. If it's always true, then your solution is just the other part. So I wouldn't call that ignoring, but I think that's what you're getting at, is it just ends up being the other thing. Yeah. So it's because if this is always true, then they're going to overlap wherever the other thing is. Yeah. Big takeaway, all the different kinds of interpretations of these questions. There's all kinds of different answers that you can get, and you really do have to get comfortable with that interpretation. Number line is a strategy that works really well that you can use, especially if it's a complicated one and a little bit of a pinch. Otherwise, if you think you can just manage the logic on your own, you can certainly do that too.